interval of the electrocardiogram. The body fluids are good conductors because the body is a volume conductor. Fluctuation in potentials representing the algebraic sum of the action potentials myocardial fibers can be recorded extracellularly. The record of these fluctuations in potential during the cardiac cycle is the ECG. The Nobel Prize in Physiology or Medicine in 1924 was awarded to William Inter-Nodal for his discovery of the mechanism of the electrocardiogram. Now let us just recapitulate about the different waves of ECG. You know, there are in the 12-lead ECG, there are 6 limb leads and 6 chest leads. 3 bipolar limb leads are lead 1, lead 2 and lead 3. Then there are augmented limb leads AVR, AVL and AVF, and the chest lead V1 to V6. This is the ECG recorded in lead 2. T wave, Q wave, S wave, R wave. Now let us just recapitulate the ECG intervals. The PR interval. Events in the heart during this interval are the atrioventricular conduction. Range is 0.1 to 2.2 seconds. QRS duration, that is the ventricular depolarization. Ranges up to 0.1 from 0.08. QT interval. Ventricular action potential. Average 0.4 up to 0.43. ST interval, plateau portion of the ventricular action potential. So we have learned about the different intervals of ECG. Now just let us recapitulate about the basic ECG graph. 1 millimeter small square. You can see the small squares. They are 1 millimeter. 5 millimeter is the large square. Speed of paper is 25 millimeter per second. The vertical lines measure the amplitude or voltage. Each small box represents 0.1 millivolt. The horizontal line measures the time. Each small box equals to 0.04 seconds. Now see this picture. The impulse originates in the AC node and then through the inter-nodal pathways they go to the AV node. From there to the bundle of his Purkinje fibers, then from the endocardium to the epicardium. The AC node acts as the pacemaker of the heart because it has got the highest rhythm. You know, other tissues also have got autorhythmicity, but as the rate of the AC node is more than others, so the heart beats at the rate of the AC node. Now let's discuss about the inter-nodal pathways and transmission of the cardiac impulse through the atria. The ends of the sinus nodal fiber connect directly with surrounding atria. atrial muscle fibers. Action potential originating in the sinus node travel outward into these atrial muscle fibers. Action potential spreads to the entire atrial muscle mass and eventually to the AV node. We have learned already about the conduction velocity of the different parts of the atria and the ventricle. So you see in this picture, there is depolarization of the AC node. Then impulses come to the AV node. Then depolarization spreads more slowly across the atria. Conduction slows through the AV node. Depolarization moves rapidly through ventricular conducting system to the apex of the heart. Depolarization wave spreads upwards from the apex. So you can see this in the diagram. Again, in this diagram, you can see how the impulse spreads from the AC node to different parts of the heart. The impulse, after traveling through the inter-nodal pathways, reach the AV node about 0.03 second after its origin. Then there is another delay of 0.09 second in the AV node itself before the impulse enters the penetrating portion of the AV bundle. A final delay of another 0.04 second occurs mainly in this penetrating AV bundle. Thus, the total delay in the AV nodal and AV bundle system is about 0.13 second. This is in addition to the 0.03 second from the AC node to the AV node. So 0.03 plus 0.13 second is equal to 0.16. This is somewhat the PR interval. The range is between 0.12 to 0.2 second. So what is this necessary, this delay? If this delay was not there, then what would have happened? The atria and the ventricle would have contracted at the same time. So the atria would not have been able to empty its blood into the ventricle. So you can see here how the impulse travels from the AC node through the atrial fibers to the AV node and finally to the ventricles. This is the graphical ECG representation, the PR interval. Now look at the picture. The first picture shows normal PR interval. In the second picture, you can see first degree heart block, then the second degree heart block, and finally the complete heart block. Prolonged PR interval may indicate heart block. Short PR interval occurs in diseases like Wolff-Parkinson-White syndrome. In first degree heart block, all P waves are followed by QRS complex. Look at the picture. All P waves are followed by QRS complex. Only the PR interval is more than 0.2 seconds. So there is increase in PR interval, but all P waves are followed by QRS complex. In second degree block, what happens? There are two types. One is Mobitz type 1 heart block, that is the Ventibach phenomena. So runs in cycle. First PR interval is often normal with successive bit PR interval lengthens until there is a P wave with no following QRS complex. Now second degree heart block. Mobitz type 2. PR interval is constant duration is normal or prolonged. Periodically, no conduction between atria and ventricle, producing a P wave with no associated QRS complex. So, this is Moby's type 2 heart block. Now, in third complete heart block, there is no relation between the P wave and the QRS complex. So there is complete heart block. So impulses are not traveling from the atria to the ventricle. So what will happen? After some time, the ventricle will start beating at its own rhythm, which is known as the idioventricular rhythm. But the brain cannot withstand hypoxia. So the person may lose consciousness. And after some time, when the ventricle overrides the atrial effects and it starts beating at its own rhythm, that is the idioventricular rhythm, then there is again blood supply that occurs. The person loses consciousness for a transient period. This is known as the Stokes-Adams syndrome.